Hi, I'm Matthew Gray. Imagine a world that looks nearly identical to our own. A world with thick white clouds drifting through a blue sky. A world where vast oceans cover the northern hemisphere and where rivers rush through green valleys carved into ancient rock. By all logic, this should be Earth. And yet, this is Mars. 4 billion years ago, the red planet was not red at all. It was a warm, wet, and dynamic world. It held more water than Earth's Arctic Ocean. It possessed a magnetic shield that protected it from the sun, and it hosted the chemistry that could have supported life. But then, the water vanished, the shield failed, and the planet died. How did a world so full of promise turn into a frozen desert? What invisible force tore away the oceans and left behind only dust? Tonight, we will travel back to the Noachian period, to see Mars as it once was. We will watch the oceans rise and the first rainstorms fall, and we will witness the invisible solar storm that stripped the planet bare. But before we begin our journey, please take a moment to like the video and subscribe. It is a simple and wonderful way to support the channel, and it means a great deal to me. I am also always curious to know where in the world and at what time you are joining me tonight. And now, settle in. Let the noise of the modern world fade away, and let us travel back to the day Mars died. To understand how Mars died, we must first understand how it was born. The story begins 4.6 billion years ago, in a cloud of gas and dust orbiting a young star. Our sun had just ignited, and the heat from its nuclear furnace sent shockwaves through the surrounding nebula. The dust began to clump. Grain by grain, the clumps grew larger. They collided and merged, building into boulders, then mountains, then planetesimals hundreds of kilometers across. Gravity did the rest. The largest objects pulled in everything around them, and within a few million years, the inner solar system contained 4 rocky worlds: Mercury, Venus, Earth, and Mars. The process of planetary formation is violent and chaotic. The early solar system was crowded with debris, the leftover material that did not get incorporated into the sun or the planets. Small objects collided and stuck together through a process called accretion. As they grew larger, their gravity became stronger, allowing them to attract even more material. But not all collisions resulted in growth. High-speed impacts could shatter objects, sending fragments flying in all directions. The largest planetesimals, those that grew to moon size or larger, dominated their orbital zones, sweeping up the smaller debris and gradually clearing their paths around the sun. This winnowing process took tens of millions of years, but eventually the 4 terrestrial planets emerged as the survivors. Mars formed in the outer reaches of the inner solar system, about 228 million kilometers from the sun. It was smaller than Earth, with only about 1/10 the mass and half the diameter. This would prove significant. A smaller planet means a smaller core, and a smaller core cools faster. But in those early days, Mars was hot. The collisions that built the planet generated enormous heat. The surface was molten rock, a global ocean of magma that glowed red and orange against the black of space. There was no atmosphere, no water, nothing but heat and violence. For the first few 100 million years, the inner solar system was a shooting gallery. The planets had swept up most of the nearby debris, but vast numbers of asteroids and comets still orbited in chaotic paths. They slammed into the planets at speeds of tens of kilometers per second. Each impact released energy equivalent to millions of nuclear weapons. The surfaces of the rocky worlds were pocked and scarred, cratered beyond recognition. This period is known as the Late Heavy Bombardment, and it peaked around 4.1 billion years ago. Mars, like Earth and the Moon, was struck thousands of times. Some of these impacts were so large that they excavated craters hundreds of kilometers across. The Hellas Basin, the largest impact structure on Mars, was formed during this time. It is 2,300 kilometers in diameter and 9 kilometers deep, carved by an object the size of Pluto's moon. But the bombardment also brought gifts. Many of the comets that struck Mars contained water ice. When they hit the hot surface, the ice vaporized instantly, releasing steam into the thin proto-atmosphere. With each impact, more water vapor accumulated. At the same time, volcanic activity was intense. Mars was geologically alive, its interior still hot from the energy of formation. Magma pushed up through cracks in the crust, building enormous volcanoes. The Tharsis region, a massive volcanic plateau, began to rise. Olympus Mons, the largest volcano in the solar system, started to form. These eruptions released not just lava, but also gases trapped in the molten rock. Carbon dioxide, sulfur dioxide, and most importantly, water vapor poured into the atmosphere. Slowly, the surface began to cool. The magma ocean solidified into a crust of basalt, dark and dense. The impacts continued, but they were less frequent now. The young atmosphere was thickening. It was not yet breathable, not even close. It was mostly carbon dioxide, with traces of nitrogen, argon, and water vapor. But it was thick enough to trap heat, creating a greenhouse effect. The surface temperature rose. And as the temperature rose, something remarkable began to happen. The water vapor in the atmosphere started to condense. Around 4 billion years ago, clouds formed for the first time in the skies of Mars. They were thin at first, wispy streaks of ice crystals high in the atmosphere. But as more water vapor rose from volcanic vents and accumulated from comet impacts, the clouds grew thicker, and then, one day, it rained. The first drops of liquid water fell on Mars, landing on ancient basalt that had never been wet. The water pooled in the lowest areas, filling impact craters and volcanic calderas. It flowed downhill, carving channels in the rock, and it kept raining. For thousands of years, perhaps hundreds of thousands, the rain fell on Mars. The northern lowlands of Mars are topographically distinct from the southern highlands, sitting an average of 5 kilometers lower in elevation. This dichotomy, whose origin is still debated, created a natural basin. As the rain fell and the water accumulated, this basin began to fill. Rivers flowed down from the southern highlands, carrying sediment and minerals. The water spread across the northern plains, creating vast, shallow seas. By the end of the Noachian period, around 3.7 billion years ago, Mars possessed an ocean. Scientists have named it Oceanus Borealis, the Northern Ocean. It covered nearly 1/3 of the planet, an area larger than the Atlantic Ocean on Earth. In some regions, it was more than a kilometer deep. Mars was blue, the skies were blue, the ocean was blue, and the planet, for a brief moment in cosmic time, looked like Earth. The formation of the ocean marked the beginning of Mars' golden age, but it did not happen in isolation. A planet is a system, and every part of that system must work together to create habitable conditions. The ocean was one piece, the atmosphere was another, but perhaps the most critical component was something invisible, something that could not be seen or touched, but without which the entire system would fail. This was the magnetic field. Deep beneath the surface of Mars, in the core of the planet, liquid iron churned. The core was hot, more than 1,000 degrees Celsius, and the iron was molten and fluid. As Mars rotated, this liquid iron flowed in complex patterns, driven by convection. Hot iron rose from the center of the core, cooler iron sank toward the bottom. This circulation created a dynamo effect, generating electric currents, and those currents produced a magnetic field. The field extended far beyond the planet itself, reaching tens of thousands of kilometers into space. It was not as strong as Earth's magnetic field, but it was sufficient. It created a protective bubble, a magnetosphere, that surrounded Mars and shielded it from the solar wind. The physics of planetary magnetic fields is well understood today, but it is worth examining in detail because it explains both why Mars had a magnetic field in the early days and why that field eventually died. The core of a terrestrial planet consists primarily of iron and nickel, metals that are dense enough to sink to the center during the planet's formation. When the planet is young and hot, this metal is liquid. The liquid iron is electrically conductive, which means it can carry electric currents. As the planet rotates, the Coriolis force organizes the convection into helical patterns, spiraling columns of rising and sinking iron. These columns generate loops of electric current, and according to the laws of electromagnetism, a moving electric charge creates a magnetic field. The more vigorous the convection, the stronger the field. On early Mars, convection in the core was driven by two main sources of heat. The first was residual heat from the planet's formation, the energy released by countless collisions during the accretion process. The second was radioactive decay. Elements such as uranium, thorium, and potassium are radioactive, meaning they spontaneously break apart, releasing energy in the form of heat. These elements were incorporated into Mars during its formation, and their decay has been heating the planet from within for billions of years. In the early days, when the concentration of radioactive elements was higher, the heat output was greater, driving more vigorous convection and a stronger magnetic field. The solar wind is a constant stream of charged particles, mostly protons and electrons, that flows outward from the sun at speeds of hundreds of kilometers per second. It is invisible, but it is powerful. When it encounters a planet without a magnetic field, it interacts directly with the atmosphere, gradually stripping away gas molecules and carrying them off into space. But when a planet has a magnetic field, the charged particles are deflected. They flow around the magnetosphere like water around a rock in a stream. The atmosphere is protected. On early Mars, the magnetic field performed this function. It kept the atmosphere intact, and the atmosphere kept the planet warm and wet. The atmosphere of ancient Mars was thicker than it is today, by a factor of perhaps 100 or more. The exact pressure is unknown, but estimates suggest it may have been comparable to Earth's atmosphere at sea level, or perhaps half that. This thick atmosphere had several effects. First, it created enough surface pressure to allow liquid water to exist. On modern Mars, the atmospheric pressure is so low that water cannot remain liquid. It either freezes or boils away instantly. But in the Noachian period, the pressure was high enough to stabilize liquid water on the surface. Second, the thick atmosphere trapped heat through the greenhouse effect. Carbon dioxide is a greenhouse gas, and with so much of it in the atmosphere, Mars retained warmth from the sun. The average global temperature may have been above freezing, perhaps as high as 10 degrees Celsius in some regions. This was cold by Earth standards, but it was warm enough for rain and rivers. The volcanic activity that released gases into the atmosphere also shaped the landscape in dramatic ways. The Tharsis volcanic province continued to grow throughout the Noachian period. This region is a massive bulge on the Martian surface, rising 10 kilometers above the surrounding plains and spanning 4,000 kilometers across. It is home to some of the largest volcanoes in the solar system. Olympus Mons, which sits on the northwestern edge of Tharsis, is 21 kilometers tall, nearly 3 times the height of Mount Everest. Its base is 600 kilometers wide, roughly the size of the state of Arizona. When it was actively erupting, it would have been visible from space, a glowing mountain of fire. But Tharsis was not the only volcanic region. Elysium Mons, another large volcano, rose in the northern hemisphere. Smaller volcanic vents dotted the highlands. These eruptions were not explosive in the way that Earth's volcanoes often are. Martian lava was more fluid, flowing across the surface in vast sheets that solidified into plains of basalt. The gases released by these eruptions continually replenished the atmosphere, replacing molecules that were lost to space or locked away in rocks through chemical reactions. As long as the volcanoes remained active, the atmosphere remained thick. Water flowed across the surface in many forms. There were rivers, some of them large, carving valleys that can still be seen today. The valley networks of Mars are most concentrated in the southern highlands, where the terrain is older and more heavily cratered. These valleys are not like the grand canyons of Earth, carved by a single large river over millions of years. Instead, they are branching networks, resembling the drainage patterns of rainfall. Water fell as rain in the highlands, flowed downhill, and merged into larger and larger channels as it descended toward the Northern Ocean. Some of these rivers may have been dozens of kilometers wide and hundreds of meters deep. They carried not just water, but sediment, rocks, and minerals dissolved from the ancient crust. At the mouths of these rivers, where they emptied into the ocean, deltas formed. Sediment settled out of the slow-moving water, building up layers of silt and clay. These deltas are of intense interest to scientists today because they are ideal environments for preserving signs of past life. On Earth, river deltas are rich ecosystems, teeming with bacteria, plants, and animals. If life ever existed on Mars, these ancient deltas are among the most likely places to find evidence. Jezero Crater, the landing site for NASA's Perseverance rover, was chosen precisely because it contains a well-preserved ancient delta. The rover is currently drilling into rocks that were once at the bottom of a lake, searching for organic molecules and other biosignatures. During this time, Mars was not just wet, it was geologically active, magnetically protected, and atmospherically stable. The conditions were as close to Earth-like as they would ever be, and for hundreds of millions of years, these conditions persisted. The Noachian period, named after the ancient region of Noachis Terra in the southern highlands, lasted from approximately 4.1 to 3.7 billion years ago. This was the era of blue Mars, the time when the planet most closely resembled a habitable world. To understand what it might have been like to stand on the surface of ancient Mars during this period, we must reconstruct the environment from the clues left behind in the rocks and minerals that still exist today. Imagine standing on a beach at the edge of the Northern Ocean. The sky above you is pale blue, though not the deep azure of Earth's sky. The Martian atmosphere, even in its thickest state, contained more dust and less oxygen than Earth's, giving the sky a slightly muted tone. Clouds drift overhead, white and wispy, carried by winds that blow from the warmer equatorial regions toward the colder poles. The temperature is cool but not frigid, perhaps 5 degrees Celsius on this particular day. You can see your breath in the air, but you do not need heavy insulation. The pressure is comfortable, roughly equivalent to standing at an altitude of 5,000 meters on Earth, like the high plateaus of Tibet. The ocean stretches before you to the horizon. It is not the dark blue of Earth's deep oceans, but a lighter, more turquoise color, tinted by the minerals dissolved in the water and the reflection of the pale sky. The water is not calm. Waves roll in, driven by the wind, breaking on the shore with a rhythmic crash. The waves are larger than you might expect. Mars rotates at nearly the same speed as Earth, and the wind patterns are similar, but the lower gravity means that waves can grow taller before breaking. These are not towering walls of water, but they are substantial, perhaps 2 or 3 meters high. The shoreline itself is a mix of sand and rock. The sand is not the white quartz sand of tropical Earth beaches. It is dark, almost black, composed of weathered basalt from the volcanic plains. Mixed with the sand are larger rocks, smooth and rounded by the action of the waves. Some of these rocks are olivine, a green mineral common in Martian basalt. Others are magnetite, dark and heavy, formed in the presence of water and iron. You pick up a piece of magnetite and feel its weight. On Earth, magnetite is often a sign of biological activity, precipitated by bacteria that use iron in their metabolism. Here on ancient Mars, the same process may have occurred. Behind you, the land rises gradually toward the southern highlands. The terrain is rough, cratered by billions of years of impacts, but the craters are softened by erosion. Rain has been falling here for millennia, and the sharp rims of the craters have been worn down. Vegetation does not cover the hills, at least not in any form we would recognize, but the rocks are stained with minerals deposited by water. Iron oxides give some surfaces a reddish tint, while carbonates, formed when carbon dioxide dissolves in water, create lighter patches of white and cream. A river flows down from the highlands, cutting through a valley that has been carved over countless years. The river is perhaps 50 meters wide and several meters deep, flowing swiftly over a bed of gravel and boulders. The water is cold, fed by melting snow and ice from higher elevations, where the temperature remains below freezing year-round. The river carries sediment, fine particles of clay and silt that cloud the water and give it a milky appearance. Where the river meets the ocean, the current slows and the sediment settles, building the delta layer by layer. This process has been going on for hundreds of thousands of years, and the delta has grown into a broad fan of land that extends into the ocean for several kilometers. The chemistry of the water is complex. It is not pure H2O, but a solution containing dissolved salts, carbonates, sulfates, and trace amounts of other minerals. The salinity is lower than Earth's oceans, which are about 3.5% salt by weight. Early Martian oceans may have been closer to 1 or 2%, brackish rather than fully marine. This lower salinity would have implications for any potential life. On Earth, life thrives in a wide range of salinities, from freshwater lakes to hypersaline lagoons. The early Martian ocean would have fallen well within the range of habitable conditions. Could life have existed in this ocean? The question is one of the most profound in planetary science. We know that life on Earth began early, perhaps as soon as conditions stabilized after the late heavy bombardment. The oldest confirmed fossils are approximately 3.5 billion years old, but chemical evidence suggests that life may have existed as early as 3.8 or even 4.1 billion years ago. This means that life on Earth emerged at roughly the same time that Mars had a thick atmosphere and a global ocean. The two planets were not so different in those early days. Both had liquid water, both had volcanic activity, releasing chemical energy, and both had the raw materials necessary for life. If life began on Earth under these conditions, there is no obvious reason why it could not have begun on Mars as well. The search for life on ancient Mars focuses on specific types of environments. Hydrothermal vents, where hot water from volcanic activity mixes with cold ocean water, are considered prime candidates. On Earth, hydrothermal vents support rich ecosystems that do not depend on sunlight. Instead, bacteria use the chemical energy from compounds such as hydrogen sulfide to drive their metabolism. Similar vents almost certainly existed on the floor of the Martian ocean. The intense volcanic activity that built Tharsis and Olympus Mons would have heated groundwater, and that water would have found its way to the surface, including the ocean floor. These vents would have been oases of warmth and chemical energy in the cold Martian sea. Another promising environment is the shallow water near river deltas. These regions would have been rich in nutrients carried down from the highlands by the rivers. Sunlight could penetrate the shallow water, and the combination of light, nutrients, and relatively warm temperatures would have created conditions conducive to photosynthesis. On Earth, photosynthetic bacteria were among the first forms of life, and they transformed the planet by producing oxygen as a waste product. If photosynthetic life existed on Mars, it may have produced oxygen as well, though probably not enough to significantly alter the atmosphere. The Martian ocean would have absorbed much of the oxygen, oxidizing iron and other metals and preventing a build-up in the air. The magnetic field that protected the atmosphere also protected any potential life from harmful radiation. The sun emits not just light and heat, but also high-energy particles and ultraviolet radiation that can damage biological molecules. On Earth, the atmosphere and magnetic field together block most of this radiation, creating a safe environment at the surface. On early Mars, the magnetosphere performed the same function, deflecting charged particles and preventing them from reaching the surface. Without this protection, life would have been forced to exist deep underground or underwater, shielded by meters of rock or water. But with the magnetic field in place, the surface and shallow waters were habitable. For perhaps 300 million years, these conditions endured. The ocean lapped at the shores of the northern plains, the rivers flowed, the rain fell. The volcanoes erupted, releasing gases that replenished the atmosphere. And the magnetic field held steady, protecting everything beneath it. Mars was not static. The climate varied, with warmer and colder periods, wetter and drier epochs. Impact events still occurred, though less frequently than before, but the basic structure of the system remained intact. Mars was a world in equilibrium, a planet where the forces of geology, atmosphere, and magnetism worked together to create stable, potentially habitable conditions. But deep below, in the core of the planet, something was changing. The peak of Mars's habitability coincided with the late Noachian period, roughly 3.8 to 3.7 billion years ago. During this time, the planet's systems were at their most stable and robust. The magnetic field was strong, the atmosphere was thick, and the ocean was at its maximum extent. To truly understand what made this era special, we must examine each component of the system in detail and see how they interacted to create a world that was, for a brief time in cosmic history, genuinely Earth-like. The magnetic field of ancient Mars was not uniform. Like Earth's magnetic field today, it had poles and an equator, regions where the field lines were vertical and regions where they were horizontal. The strength of the field varied across the surface, with the strongest regions located above the most active parts of the core. Measurements from orbit, taken by spacecraft such as Mars Global Surveyor, have revealed that the ancient magnetic field left a permanent imprint in the Martian crust. When volcanic rocks cool below a certain temperature, they lock in the direction and strength of the magnetic field at the time of their formation. This remnant magnetism can still be detected today, billions of years after the field itself ceased to exist. The strongest remnant fields are found in the southern highlands, particularly in regions such as Terra Cimmeria and Terra Sirenum. These regions contain rocks that were magnetized during the Noachian period, when the dynamo in the core was still active. The presence of a magnetic field had profound effects on the upper atmosphere. When charged particles from the solar wind encountered the magnetosphere, they were deflected away from the planet, flowing around the magnetic bubble and continuing out into space. Some particles did enter the magnetosphere, particularly near the poles, where the field lines converge and create openings. These particles interacted with the upper atmosphere, exciting atoms and molecules and causing them to emit light. On Earth, this process creates the aurora borealis and aurora australis, the northern and southern lights. Ancient Mars almost certainly had auroras as well, glowing curtains of green and red light that danced in the skies near the poles. An observer standing in the northern lowlands, near the shore of the ocean, might have seen these lights on clear nights, shimmering and shifting as the solar wind ebbed and flowed. The composition of the atmosphere during the late Noachian was dominated by carbon dioxide, which made up perhaps 95% of the total. Nitrogen was the second most abundant gas, at a few percent, followed by argon, a noble gas that does not react chemically and serves as a stable tracer of atmospheric history. Water vapor was present in variable amounts, depending on the season and location. Near the ocean and in the river valleys, humidity was high and clouds formed readily. In the drier highlands and polar regions, the air was more arid. The total atmospheric pressure was likely between 0.5 and 1 bars, or about half to equal the pressure at Earth's surface. This is sufficient to allow liquid water to exist and to create a greenhouse effect strong enough to keep the planet warm. The greenhouse effect on Mars was weaker than on Venus, but much stronger than on modern Mars. Carbon dioxide is not the most potent greenhouse gas, but in sufficient quantities, it can trap significant amounts of heat. The thick atmosphere absorbed infrared radiation emitted by the surface and re-radiated some of it back down, warming the planet. The average global temperature during the late Noachian may have been around 0 to 5 degrees Celsius, cold by human standards, but well above the freezing point of water in many regions. The equatorial zones would have been warmer, perhaps 10 to 15 degrees during the day, while the polar regions remained frozen year-round. Seasonal variations were significant. Mars has a similar axial tilt to Earth, about 25 degrees, which creates distinct seasons. During the southern summer, when the southern hemisphere was tilted toward the sun, the highlands would have experienced their warmest temperatures. Ice caps at the poles would have partially melted, releasing water vapor into the atmosphere and increasing cloud cover. The ocean itself was a dynamic system. Currents circulated the water, driven by differences in temperature and salinity. Warm water from the equatorial regions flowed northward, carrying heat toward the poles. Cold water from the poles sank and flowed southward along the ocean floor, creating a deep circulation pattern. This thermohaline circulation is similar to the ocean currents on Earth that redistribute heat around the globe. On Mars, these currents would have moderated the climate, preventing the equator from becoming too hot and the poles from becoming too cold. The depth of the ocean varied. In the deepest parts of the northern basin, it may have reached 1.5 kilometers or more. In the shallowest areas, near the shorelines and deltas, it was only a few meters deep. These shallow regions were where the most interesting chemistry occurred. Sediments carried by the rivers settled in the deltas and shallow seas, creating layers of clay and silt. These sediments are of great interest because clays are excellent at preserving organic molecules. On Earth, ancient clays have yielded fossils and chemical traces of life dating back billions of years. The clays on Mars formed in the presence of liquid water, and their mineral composition provides clues about the pH and chemistry of the water. Smectite clays, which are common in the Noachian terrains, form in relatively neutral to alkaline conditions, the kind of environment that is most hospitable to life. If microbes lived in the Martian Ocean, they may have left behind traces locked in these clays, waiting to be discovered. The chemistry of life, as we understand it, requires a few essential elements. Carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur are the 6 most important, often abbreviated as CH-NOPs. All of these elements were present on ancient Mars. Carbon was abundant, both in the atmosphere as carbon dioxide and dissolved in the water as carbonic acid and carbonates. Hydrogen was present in water. Nitrogen was in the atmosphere, and it would have been incorporated into the ocean through reactions with minerals. Oxygen was available in water and in oxidized minerals. Phosphorus, which is rarer, would have been released from rocks through weathering and carried into the ocean by rivers. Sulfur was abundant, released by volcanic eruptions as sulfur dioxide and deposited in the form of sulfates. The delivery of phosphorus is particularly interesting because it is often the limiting nutrient for life. On Earth, phosphorus is essential for DNA, RNA, and ATP, the molecule that cells use to store and transfer energy. Phosphorus does not form many soluble compounds, which means it does not easily dissolve in water. Most of the phosphorus on a planet is locked up in rocks as phosphate minerals, such as apatite. For life to access this phosphorus, the rocks must be weathered by water and acids, breaking down the minerals and releasing phosphate ions into solution. On Mars, this weathering would have occurred in the river valleys and deltas, where flowing water ground down the rocks and carried the dissolved phosphate into the ocean. The rate of phosphorus delivery would have depended on the intensity of rainfall and river flow, both of which were at their peak during the Noachian period. In addition to these elements, life requires energy. On Earth, organisms obtain energy in two main ways: photosynthesis, which uses sunlight, and chemosynthesis, which uses chemical reactions. Both pathways would have been available on Mars. Sunlight reached the surface, though it was weaker than on Earth, due to Mars's greater distance from the Sun. Mars is 1.5 astronomical units from the Sun, compared to Earth's one, which means it receives only about 43% as much sunlight. This is still sufficient for photosynthesis. On Earth, photosynthetic organisms thrive in low-light environments, such as deep in the ocean or under thick ice. Chemosynthesis, which does not depend on light, would have been even more viable. The hydrothermal vents on the ocean floor would have provided a steady supply of chemical energy in the form of reduced compounds like hydrogen and methane. The presence of liquid water, the right chemistry, and sources of energy are the three key ingredients for life. Ancient Mars had all three. This does not prove that life existed, but it demonstrates that the conditions were suitable. The question of whether life actually arose is one that may only be answered by finding direct evidence, such as fossils or biomarkers in the rocks. Several missions have been sent to Mars to search for such evidence. The Curiosity rover, which landed in Gale crater in 2012, has found organic molecules, complex carbon-based compounds that could be biological in origin or could have been produced by non-biological processes. The Perseverance rover, which landed in Jezero crater in 2021, is drilling into rocks from the ancient delta and storing samples for future return to Earth. If life existed in that delta 3.7 billion years ago, Perseverance may have already collected the evidence. But even as Mars reached its peak habitability, the forces that would destroy it were already in motion. The magnetic field, the shield that protected the atmosphere and made the surface habitable, depended on a single factor: the heat in the planet's core, and that heat was slowly, inexorably draining away. The magnetic field of a planet is generated by a dynamo in its core. This dynamo requires three things: a liquid, electrically conductive medium, usually molten iron; convection, where hot material rises and cool material sinks; and rotation, which organizes the flow into coherent patterns. On Earth, all three conditions are met. The outer core is liquid iron, convection is driven by heat from the inner core and radioactive decay, and the planet's rotation is fast enough to sustain the dynamo. As long as these conditions persist, the magnetic field remains stable. But on Mars, the situation was different. Mars is smaller than Earth, with a radius of 3,390 kilometers compared to Earth's 6,371 kilometers. Its mass is only 11% of Earth's mass. This means that Mars has a much smaller core, and a smaller core has less volume relative to its surface area. Heat escapes more quickly from a small object than from a large one. This is a basic principle of thermodynamics. A cup of hot coffee cools faster than a large pot of hot soup because the coffee has more surface area per unit of volume. The same principle applies to planets. Mars's core was hot when the planet formed, heated by the energy of colliding planetesimals and the decay of radioactive elements. But from the moment of formation, it began to cool. For the first few 100 million years, the cooling was slow. The core remained above the melting point of iron, and convection continued. The liquid iron churned, generating electric currents and sustaining the magnetic field. But by around 4 billion years ago, the core had cooled enough that convection began to weaken. The temperature difference between the hot interior and the cooler outer regions decreased, and with it, the driving force for convection diminished. The flow of liquid iron became slower and less organized. The electric currents weakened, and the magnetic field began to fade. This process was gradual, not sudden. The magnetic field did not disappear overnight. It weakened over millions of years, slowly declining in strength until it could no longer protect the atmosphere. The exact timeline is uncertain, but evidence from the remnant magnetism in the crust suggests that the field was still active at 4.1 billion years ago and had largely vanished by 3.7 billion years ago. This means the magnetic field lasted for perhaps 400 million years after the planet's formation, long enough to allow the ocean and thick atmosphere to develop, but not long enough to sustain them indefinitely. The consequences of losing the magnetic field were not immediately apparent. The atmosphere did not vanish the moment the field died. For a time, perhaps tens of millions of years, the planet continued much as before. The ocean was still there, the rivers still flowed, the rain still fell. But without the magnetic shield, the solar wind now had direct access to the upper atmosphere, and slowly, inexorably, it began to strip away the gases. The solar wind is a stream of charged particles, mostly protons and electrons, ejected from the sun's outer atmosphere. It moves at speeds between 300 and 800 kilometers per second, carrying energy and momentum far into the solar system. When these particles encounter an unprotected atmosphere, they collide with the gas molecules in the upper layers. These collisions transfer energy to the molecules, and if the energy is sufficient, the molecules can be accelerated to escape velocity. This process is called sputtering, and it is the primary mechanism by which Mars lost its atmosphere. Sputtering is not the only mechanism of atmospheric loss. Another process, called photochemical escape, occurs when ultraviolet light from the sun breaks apart molecules in the upper atmosphere. On Mars, water vapor is particularly vulnerable. When a water molecule absorbs a high-energy ultraviolet photon, it can split into hydrogen and oxygen atoms. The hydrogen atoms, being very light, can reach escape velocity simply through thermal motion and drift off into space. The oxygen atoms, being heavier, typically remain in the atmosphere or react with the surface, but some can also escape if they are given enough energy. This dissociation and escape of water has been happening on Mars for billions of years, gradually removing hydrogen and leaving the planet drier. Thanks for watching, and have subscribed to the 5. See you next time. Subscribe to likes. Sputtering is not a fast process. It does not remove large amounts of gas all at once. Instead, it erodes the atmosphere slowly, molecule by molecule, over millions of years. The lighter molecules, such as hydrogen and helium, are lost more easily because they move faster at a given temperature and require less energy to reach escape velocity. Heavier molecules, such as carbon dioxide and nitrogen, are lost more slowly. But over geological time, even the heavy molecules are removed. The rate of loss depends on several factors: the density of the solar wind, the temperature of the upper atmosphere, and the strength of the planet's gravity. Mars's gravity is only 38% of Earth's, which makes it easier for molecules to escape once they have been energized. NASA's MAVEN spacecraft, which has been orbiting Mars since 2014, has measured the current rate of atmospheric loss. Today, Mars loses about 100 grams of atmosphere per second to the solar wind. This sounds like a small amount, but over billions of years, it adds up. If the current rate of loss has been roughly constant since the magnetic field died, Mars would have lost the equivalent of several bars of atmospheric pressure, more than enough to account for the difference between the thick atmosphere of the Noachian period and the thin atmosphere of today. However, the rate of loss was probably not constant. When the magnetic field first failed, the atmosphere was thicker, which would have increased the rate of sputtering. Additionally, the young sun was more active, producing stronger solar wind and more frequent solar storms. During periods of intense solar activity, the rate of atmospheric loss would have been much higher, perhaps 10 or 100 times the current rate. As the atmosphere thinned, the greenhouse effect weakened. With less carbon dioxide to trap heat, the surface temperature began to drop. The first sign of trouble would have been in the polar regions, where temperatures were already marginal. Ice caps that had partially melted during the summer stopped melting. They grew thicker and more permanent. The equatorial regions remained warm enough for liquid water for a time, but even there the climate was shifting. Rainfall became less frequent. Rivers that had flowed year-round began to dry up during the colder seasons. The ocean, which had been fed by these rivers, received less inflow. At the same time, water was being lost from the ocean itself. Some of it evaporated into the atmosphere and was lost to space through the same sputtering process that removed other gases. Some of it froze, forming ice on the surface of the ocean and along the shorelines. The transition from the Noachian period to the Hesperian period, which began around 3.7 billion years ago, marks the point at which the climate of Mars shifted from wet to dry. The ocean was still present, but it was shrinking. The atmosphere was thinning, and the magnetic field was gone. The planet had crossed a threshold from which there was no return. The Hesperian period, lasting from 3.7 to 3 billion years ago, was the era of Mars's decline. During this time, the planet transformed from a wet world with a thick atmosphere to a cold, dry desert. The changes were gradual, but relentless. Each passing million years saw the atmosphere grow thinner, the temperature drop lower, and the water disappear from the surface. By the end of the Hesperian, Mars resembled the planet we see today, a frozen wasteland where no liquid water can exist. The loss of the atmosphere occurred in stages. First, the lightest gases were stripped away. Hydrogen, which had been abundant in the early atmosphere, as water vapor dissociated under ultraviolet light, was lost almost entirely. This loss of hydrogen had a cascading effect on water. When water molecules in the upper atmosphere are broken apart by solar radiation, they split into hydrogen and oxygen. The hydrogen escapes to space, but the oxygen, being heavier, remains behind. Some of this oxygen reacted with iron in the Martian crust, forming iron oxides, rust. This is why Mars turned red. The planet's surface is covered with iron oxide dust, the remnant of a time when free oxygen was present in the atmosphere. As the hydrogen was lost, water could no longer be replenished in the atmosphere. The water cycle broke down. On Earth, water evaporates from the oceans, forms clouds, falls as rain, and returns to the ocean through rivers. This cycle can continue indefinitely as long as the atmosphere retains water vapor. But on Mars, the water vapor was being lost to space faster than it could be replenished. The clouds thinned. Rainfall became rare, then stopped altogether. The rivers dried up, leaving behind empty channels carved into the rock. These channels are visible today, winding across the surface like the ghosts of rivers that once flowed. The ocean itself began to shrink. Without inflow from rivers, and with water being lost to evaporation and escape to space, the water level dropped. The shoreline retreated inward, exposing the shallow regions that had once been underwater. The exposed sediments dried and hardened, preserving the record of the ocean's existence in the form of ancient lake beds and delta deposits. In the deepest parts of the basin, the ocean persisted longer, but eventually even these regions began to freeze. As the atmospheric pressure dropped below a critical threshold, liquid water could no longer exist at the surface. The remaining water either froze into ice or sublimated directly into vapor, bypassing the liquid phase entirely. The freezing of the ocean was not uniform. Ice formed first in the polar regions and at high elevations, where temperatures were coldest. As the ice expanded, it covered more and more of the ocean surface. The ice was not pure water ice. It contained salts and other dissolved minerals, which lowered its freezing point and created a mixture of ice and brine. Some of this brine may have remained liquid even as the temperature dropped below 0 Celsius, trapped in pockets within the ice. But eventually, as the temperature continued to fall, even the brine froze solid. Not all of the water was lost to space or frozen on the surface. A significant amount sank into the ground, filling pores and fractures in the rock. Mars's crust is porous, and groundwater can penetrate deep into the subsurface. As the surface water disappeared, the groundwater remained, trapped beneath a layer of frozen soil known as permafrost. This subsurface ice is still present on Mars today. Radar instruments on orbiting spacecraft have detected vast deposits of ice buried beneath the surface, particularly in the polar regions and mid-latitudes. The volume of this subsurface ice is estimated to be equivalent to a global layer several tens of meters deep, enough to fill the ancient ocean if it were melted. Volcanic activity continued during the Hesperian period, though it was less intense than during the Noachian. The eruptions released gases into the atmosphere, temporarily slowing the rate of loss. But without a magnetic field to protect the atmosphere, these gases were also stripped away by the solar wind. The net result was a slow, steady decline in atmospheric pressure. By the end of the Hesperian, the pressure had dropped to a few percent of its peak value, perhaps 50 to 100 millibars, comparable to the pressure at an altitude of 30 kilometers on Earth. At this pressure, water cannot exist as a liquid. It either freezes or boils, depending on the temperature. Mars had crossed another threshold. The planet was now too cold and the pressure too low for liquid water. The climate became hyper-arid. Precipitation of any kind, whether rain or snow, became almost non-existent. Dust storms, however, became more common. With the surface now dry and the winds no longer dampened by moisture, dust was easily lifted into the thin atmosphere. These storms could grow to enormous size, occasionally engulfing the entire planet in a shroud of red dust. The dust absorbed sunlight, warming the atmosphere and creating high-altitude winds that transported the dust around the globe. When the dust settled, it formed a layer of fine powder that covered the surface, burying the ancient rocks and erasing the details of the Noachian landscape. If life had existed on Mars during the Noachian, it faced a stark choice during the Hesperian: adapt, migrate, or die. Surface life would have been impossible as the water disappeared and the temperature plummeted. Any organisms that depended on liquid water at the surface would have perished. But life is resilient. On Earth, microbes survive in the most extreme environments, from the dry valleys of Antarctica to the deep subsurface, kilometers beneath the ground. If Martian life followed a similar pattern, it may have retreated underground, following the water as it sank into the crust. There, protected from the harsh surface conditions and supplied with liquid water from geothermal heat, life could have persisted. Whether it did is unknown, but the possibility remains. By 3 billion years ago, the transformation was complete. The Hesperian period gave way to the Amazonian period, which continues to the present day. Mars was no longer a blue world. It was red, cold, and dry. The ocean was gone, replaced by frozen plains and dust-covered lowlands. The rivers had vanished, leaving only their empty channels as evidence of the water that once flowed. The thick atmosphere had been stripped away, leaving behind a tenuous envelope of carbon dioxide at a pressure less than 1% of Earth's atmosphere. And the magnetic field, the invisible shield that had once protected it all, remained silent in the planet's dead core. Today, Mars is a silent desert. The average surface temperature is minus 60 degrees Celsius. The atmospheric pressure is 6 millibars, less than 1% of Earth's. Water cannot exist as a liquid anywhere on the surface. The sky is not blue but a pale butterscotch colour, tinted by the ever-present dust. And yet, for all its harshness, Mars is not a dead world. It is a world of frozen potential, a planet that once had oceans and may someday have them again. The story of Mars's water is written in the rocks and the landscapes that rovers and orbiters have explored for decades. The Viking landers, which touched down in 1976, were the first to search for signs of life, conducting experiments to detect biological activity in the soil. The results were ambiguous, neither confirming nor ruling out the presence of life. Since then, a succession of missions has revealed more of the planet's history. Mars Global Surveyor mapped the magnetic anomalies in the crust, providing evidence of an ancient magnetic field. Mars Odyssey detected vast deposits of subsurface ice. The Spirit and Opportunity rovers found minerals that form only in the presence of liquid water. Curiosity discovered organic molecules in ancient lake deposits. And Perseverance is now collecting samples from the delta in Jezero crater, rocks that may contain the most direct evidence yet of past life. The subsurface ice is one of Mars's most valuable resources. It represents the remnants of the ancient ocean, locked away beneath the surface and waiting to be tapped. Future human missions to Mars will depend on this ice for water, oxygen, and rocket fuel. Melting the ice and purifying the water is far easier than transporting water from Earth. The presence of subsurface ice also has implications for the search for life. If liquid water exists anywhere on Mars today, it is likely deep underground, heated by geothermal energy or chemical reactions. These subsurface habitats could be the last refuge of Martian life, if it ever existed. The question of why Mars lost its magnetic field while Earth retained its is one of the central mysteries of planetary science. The answer lies in the details of planetary formation and evolution. Earth is larger, which means its core cools more slowly. Earth also has a solid inner core and a liquid outer core, a structure that enhances the dynamo effect. Mars may have had a similar structure early in its history, but as the core cooled, the inner core solidified more quickly, reducing convection and weakening the magnetic field. Additionally, Earth benefits from tidal heating caused by the Moon. The gravitational interaction between Earth and the Moon generates friction in the Earth's mantle, adding heat to the system and prolonging the dynamo. Mars has no large moon. Its two small moons, Phobos and Deimos, are too tiny to produce significant tidal heating. The loss of Mars's atmosphere is a cautionary tale for Earth. Our planet's magnetic field protects us from the solar wind, but it is not eternal. The dynamo in Earth's core will eventually shut down, perhaps in 1 billion years or more, and when it does, our atmosphere will begin to erode. The process will be slow, far too slow to affect human civilization, but it is a reminder that planetary habitability is fragile and temporary. Mars shows us what happens when a planet loses its shield. There is also hope in the story of Mars. The water is not truly gone. It is frozen beneath the surface and locked in the polar ice caps. If Mars could be warmed through natural processes or human intervention, the ice could melt and liquid water could return to the surface. Some scientists have proposed schemes to terraform Mars to transform it into a more Earth-like world. These ideas involve releasing greenhouse gases to thicken the atmosphere, melting the ice, and restarting the water cycle. Whether such projects are feasible or desirable is a matter of debate, but they illustrate an important point. Mars was once habitable, and it could be again. The rovers that crawl across the Martian surface today are exploring a world that died 3 billion years ago. They drive across ancient lake beds and climb hills that were once islands in a vast ocean. They drill into rocks that formed underwater and analyze minerals that crystallized in the presence of liquid water. Each discovery adds another piece to the puzzle, bringing us closer to understanding what happened and why. The answer to the question of whether life existed on Mars may lie in the samples that Perseverance is collecting, samples that will be returned to Earth in the 2030 seconds and analyzed in laboratories with instruments far more sophisticated than anything that can be sent to Mars. And so our story of Mars comes to a close. It has been a true pleasure to be your guide through the rise and fall of an ocean world, from the violent birth of a planet to the silent desert it became. The story of Mars is also the story of Earth, a reminder that habitability is not guaranteed and that the forces that shape planets are powerful and indifferent. Thank you for listening. Until our next journey into the cosmos, I wish you a calm and peaceful night.